Take a moment and imagine your worst day. It could be in the office, at school, around your home. At times like these, sometimes all we want to do is hide in our bed and wait for it all to pass. But what if we couldn't even do that? This was the reality for the people of Haiti in 2010, when an earthquake equivalent in energy to 180,000 metric tons of TNT, with the power to run nearly 200,000 North American homes for a year, devastated their nation, their beds included, to the ground. Enter my research, where a younger, less graduate life stressed in high school me was inspired by this tragedy to prevent damages like these from occurring again, and all by gluing soil grains together. Let me explain. There are many factors that contribute to the overall catastrophe of an earthquake. One such is soil liquefaction. It is a way in which the strength of a soil, particularly water-saturated sandy soils, goes to zero. Under the sudden force of an earthquake, water is squeezed between soil grains and acts as a lubricant, causing the grains to lose cohesion, and as a result, the ground to flow. As a result of this, buildings tend to settle into the ground or topple over, irregardless of how well they are built. The sinking of our foot, placed on a wet, sandy patch of beach while walking, is an example of this process many of us in the audience have likely experienced. So, by gluing soil grains together, we turn many tiny parts into a single solid foundation incapable of movement. Now, many chemicals can achieve this: expansive foams, plastics, cements. However, these leach potentially toxic chemicals, block surface water, and are essentially permanent. My process is an eco-friendly one, and it works, all by mixing a common garden bacteria with urea and a calcium salt. The product, as highlighted on the left side of our slide, is a strong but porous carbonate matrix of calcium that forms around and between soil grains and bacteria, kind of like a porous marble. All in a day, no harsh chemicals, capable of water flow, naturally strong. Flash forward 6 years, a National Science Fair title and honors and a master's degree later, and the project continues to move forward. In fact, today we are changing the bacteria we use at the genetic level to make it a gluing or hardening powerhouse. More efficient, less time, stronger product. At best, we've achieved soil strengths greater than 10 times that of unhardened soil, as highlighted on the right side of our slide, and many times more with a week of curing. We want to do better, though. After all, they may say that's how the cookie crumbles, but they'll be saying that's how the building didn't tumble if I have anything to say about it. Thank you. And if there's any questions. No? Okay. Is there one? Oh, wonderful.
Cement, which is the percentage of your natural cementation with the bacteria between the grains?
So if I understand it correctly, what is the percentage of cement between my soil grains?
The percentage of the strength of your bacteria connection compared to the cement connection.
Of like Portland cement, etc. It's not quite there yet, at least not in the industrial application, but it is possible to reach those strengths after a couple of weeks of curing. We want to do better though, so yeah. Sure.
Is it possible for life to still exist if it's all glued together?
That's a very good question. So can life still exist? For example, tree roots, that could be an issue. Of course, with any cementing process, you're going to have a concern about being able to maintain the natural flora in a soil. So yes, that would be something that would unfortunately be detrimented with this. However, similar to plastics or cements, we would expect the same thing. This may be able to offer a little bit more porosity in the soil for life. Good question.
Discipline of study?
So my undergrad was in biomedical science, and my master's is in earth science. Yeah, with a joint in civil engineering. Yeah, thank you. Cool.